until 3 o'clock.
Hello and good afternoon. Welcome to the session on refrigerants and technologies. In this session, we have 4 talks today. And first one is presented by Dr. Maxim Telzin. He is an associate professor at Bauman Moscow State Technical University. He specializes in thermodynamic analysis of low temperature systems, specifically in statistical entropy. He also works in low temperature generation and application in engineering, and author of about 15 scientific publications. So Maxim, kindly share your screen and please start with the talk.
Dear colleagues, I am glad to be here and represent results of work which was. Firstly, I would like to briefly describe entropic and statistical method of the analysis. Real processes in refrigeration plants are reversible and non equilibrium. The reason of reversibility is a finite difference in mass streams potentials, like temperature difference, pressure difference, etc. Due to processes non-equilibrium, the measure of reversibility is entropy production. This method is based on both first and second law of thermodynamics, Buist-Stadova theorem, property of entropy additivity. Distribution of energy expenses for entropy production compensation for one-stage refrigeration cycle is shown on this slide. Ideal Carnot cycle is shown C1, C2, C3, C4 is totally reversible. It means that work which is spent for cold generation will be minimum and is expressed by the area as I already shown, C1, C2, C3 and C4. Real cycle is expressed by the area 1, 2, 3, 4, 5, 6. Work which is necessary for entropy production compensation in compressor is expressed by area D, E, E3, E2. Area E3, 2, 3, 4, E1, or equal to it in size EF, E4, E3, EF, E4, E3, this area, express works which is necessary for entropy production compensation in condenser. Work which is necessary for entropy production compensation in evaporator is expressed by area CD, E2, C2. In throttling devices by area AB, C3, U1. Total real work for single-stage refrigeration cycle is expressed by the sum of areas. Several equations are given on this slide. The degree of thermodynamic efficiency is determined as a relation between minimum work which is necessary for cold generation, to real compressor work. CUP values determine as relation between specific mass cooling capacities multiplied by relative mass flow and actual compressor works. The calculation method is described in conference paper in more details. We analyze two refrigeration systems for retail application. One of them is a transcritical refrigeration plant with parallel compression and ejector with two temperature levels, low temperature and medium temperature level. And second system is a well-known system, consists of two independent systems. First, for medium temperature, is based on single-stage refrigeration cycle with single throttling, and second system for low temperature level is based on cycle with economizer. This system is very known, and I won't be tell about it more. Initial date is shown on this slide. The values of refrigeration capacity, cooling capacities, like 70 kilowatts for low temperature level and 360 kilowatts for medium temperature level, is taken from existed hypermarket. Minimum condensing temperature are taken from manufacturer producers. On this slide, you can see as initial data is ambient temperature changes during 1 year. There is hour and temperature with exact hours. This data were taken from Meteonom software. The entropic efficiency of compressors are shown on this slide. This data were taken from compressor manufacturer software as average statistical data. Energetic losses changes at system components expressed in percentages of compressor work are shown on this slide. You can see different energetic losses during compressor, condenser, evaporator, and throttling for different systems. System 1 with CO2 and with R44A. On this slide you can see COP values. It's adiabatic COP and actual value of COP for two different systems. This is for R44A and this is for those 44A. This is for CO2, this is for CO2. Now you can see analysis results. As you can see, COP at adiabatic compression 6.57 for 61 CO2, 7.33 for R44A, actual value of COP 4.3 and 4.19 for R44A, degree of thermodynamic efficiency in percent 18.82 and 17.21 for R44A system 2. On this slide you can see energetic losses by system components in percent of compression work. And as you can see, system 1 compression work is more or less the same, and the most energetic losses is in throttling devices in transcritical refrigeration plant. Some conclusions. The application of this entropic and statistical method of the analysis allows for cooling plants' energy efficiency to be increased based on information about losses in different refrigeration plant components and for measures to be taken to increase the operational efficiency. The average actual value of COP for the period under review for System 1, CO2, and System 2, R44A, are comparable. The difference between these values is not more than 2.61%. Average meaning of degree of thermodynamic efficiency for transcritical refrigeration plant CO2 more than for refrigeration plant works with R44A at 8.58% for the period under review. There are small references, and I would like to pay attention on this one. It calls for not really usable exergy variant of thermodynamical analysis of low temperature system, because I was asked about why this method, entropic and statistical, more preferable than exergy variant, and you can find answer on this reference. So, thank you for your attention. If you have question, please ask. I'm ready to answer. Thank you.
Thank you, Maxim. Let's look at Slido to see if there are any questions. So there are no questions from the participants. In the panel itself, does anybody have any question for Maxim?
Sorry, are you able to hear me?
Yes, Professor
Okay.
Gordon, if you have a question, please go ahead.
Yes. Thank you, Maxim, for the presentation. I have some questions. The thing is, well, first you present, let's say, the cycle analysis and the irreversibilities evaluation, let's say. But in the end, you say actual value when you compare both systems, System 1 and System 2. Actual value means that this is experimental. I mean, it's the measurement of the cooling of the coal generated and the energy consumptions.
Yes. Yes, you're right. Do you hear me?
Yes, we hear you.
Yes,
We
you're right.
hear you, but your video is turned off. If possible, can you turn it on? Yes, we see you now. Thank you.
Okay.
So in this method, we use two kinds of COP. One of them is a theoretical part, which is calculated by using adiabatic work. And second one is the real work, which you can measure by using devices.
Okay. And so the actual values are the ones measured.
Yes.
So okay. I have, because the theoretical one, is going to be very dependent on the characterization of the component. So, and one of which is the most important is the compressor. And you presented, and it is in the paper, the efficiencies of the compressor, but there are some regions which are strange. So, for instance, there is a flat region for one of the refrigerants and not for the other one. Which looks like it is independent on the ambient temperature. Mm-hmm. So what's the reason for that?
Mm-hmm. There is just simple explanation, because for each compressor we have envelope and we have minimum available condensing pressure, condensing temperature. And that's why on this area we have a flat. So we can reduce below this value.
Okay, so pressure ratio is the same, so you are keeping same, let's say, conditions.
Yes, we have to do it.
Okay. Well, Sam, I think we have to go into the next one. I think it is time to go into the next one, so we can accumulate questions maybe for the end of the session.
Sure. I had a question and I'll ask you after all the presentations are done. So thank you very much for your talk, and let's move on to the next. So our next presentation is titled Algorithm-Based Optimization for Energy Efficient Operation of Refrigeration Systems. It is presented by Mr. George Benz. He has done his BH from University of Science in Electrical Engineering and Information Technology, followed by his master's at University of Ravensburg, Germany. He's currently a project manager, sales support at NG Refrigeration MBH, and is also working on a cooperative PhD program at Technical University of Munich. His, I think, research emphasis is on mathematical optimization and systems simulation and modeling. So George, please go ahead with your talk. Thank you.
Yeah. Oh.
We can see your screen. Thank you.
Oh, okay. Yeah. Thank you for introducing, and thank you for joining my talk today. Yeah, as you introduced me, my name is Jörg Benz, and together with Professor Christian Schweigler, I'm doing research on the algorithm-based optimization for energy-efficient operations of refrigeration system. Yeah, we are working on the Munich University of Applied Science in the Department of Building Services Engineering. And we are specifically working on the research institute Cenergy. It's a pretty new institute, the Center for Energy Efficient Buildings and Districts. Today, I would like to talk a little bit about the motivation for our research project. And then I would like to introduce to you the ENOS, the Energy Optimization Tool. It's a software what we are still developing. And then I would like to go a little bit more into the details and the data workflow of this optimization process. Then I would like to show you the test system where we are doing the validation for this software. And then again, I would like to go a little bit more into detail with the mixed integer nonlinear programming, so the optimization algorithm we are using. And last but not least, I would like to show you some results, what is actually possible while performing this optimization. The motivation is because of the fact that refrigeration systems are mostly complex and have a high number of degrees of freedom, and therefore an optimization of the plant operation requires a deep understanding of the system, and also therefore that's why optimized control requires individual programming and is applied to large-scale systems only, like for power generation systems. That led us to the idea to come up with a modular optimization tool to make optimization also available for small-scale systems. Yeah, as I mentioned previously, this ENOS is a software tool. The core or the heart of this software tool builds this solver, which is actually performing the optimization or is solving the optimization problem. This solver is fed by some input data, for example, a system configuration. That's how the individual system components are arranged to each other, for example. And we further have the plant parameters, which are represented as polynomials and include the system characteristics of the components. And then we have an actual data, which is fed by the process control of the system. So this process control is collecting all the measurement data from the real system on site or of the refrigeration system. It's collecting them, the data, and giving it also to the solver. Further, we have some optional inputs like a smart grid to take into account the actual electricity prices, or to take into account the weather data or energy demand for the system, to give this system the opportunity to look a little bit into the future and adjust the operation of the system according to the outer requirements or the outer data. Yeah. So then this solver is optimizing the system, taking into account all the stages, and create some results, which is more or less are optimized set points for the systems or for the system components. They are sent then to the process control, where the process control can distribute optimized set points to the refrigeration system itself. Since the modeling of the system or the system components are often not that accurate, and the system component or characteristic can change over time during to some if for example, if the heat exchangers are getting dirty or something, so the characteristics can change, and that's why we came up with a functional analysis to tune the models during the operation and to always fit the exact or the reality of the system. Okay, then data workflow is we start with simplified models for this refrigerant for this refrigeration components. Here, as a very simple example, the chiller. It's like it's from the canonical factor. Yeah. So of course we have for each component we have some models for the chillers, for the heat rejection, for the pumps, for the storage, and that, etc. So we are taking then those simplified models and start the simulation across the whole area of operation of the designated area of operation for the system components, which lets us then to a simulation database. And with this simulation database, we can start a regression and create some polynomials which represent then the characteristics of these components. When the software tool is connected to the real system itself, then we are starting to collecting the data of the real plant, and measuring this data, and create an operational database. And not lose the previous characteristics. We are combining the operational data and the simulation data, and as I previously mentioned, we are adjusting the simulated data to the reality. And then again and again, we are doing the regressions and always working with the newest polynomials in this case. Those polynomials are then fed into this optimization model, and together with the system configuration, the parameters for the system, and the time series or the according time series, we can create this optimization model, which then can be solved with some few solvers are actually available to solve this kind of models. And after the solve, we are getting to this optimized operation of the system. Yeah. So the test system looks as follows. So we have a small chilled water supply system with 2 chillers, and each chiller has some variable speed compressors with roughly 1.5 megawatts each. And we have a huge heat rejection plant, which can be operated dry and wet. And we have also 3 big fans in this heat rejection plant. And we have all pumps are also variable speed drives. And then we have a storage. And yeah, so this simple system has a lot of, even this simple system has a lot of degrees of freedom, like all the volume flows through the system, the temperatures in the system, and also the operational states, like which chillers should be operated, how many chillers should be operated, should we use free cooling, or should we operate the heat rejection plant dry or wet? All that stuff needs to be taken into account, or at least can be taken into account if you're willing to optimize it, which then leads us to the mathematical representation, how to do that. So as I mentioned previously, we decided to optimize like all the stages or all potentials in the system. We need to have this mixed integer nonlinear programming optimization, which has the general form, like the minimization of a nonlinear function, with also taking into account some inequality constraints, some equality constraints, also the lower and upper bounds for the variables, and additionally we introduced some binary decision variables to take the switching on and off of the components into account. This leads us to the generalized objective function, which is the minimization of the total electricity demand consumption. This electrical consumption is represented by these polynomials. So each component has its own polynomial with if you want to have some details, you can see it here. So these polynomials are, or each polynomial has its own independent variables and dependent variables, or the dependent variable, of course, is the electrical power consumption. And here you see, to connect all those electrical consumptions, you connect them with the decision variables, which can be optimized, and then also the solver can switching on and off these components during the optimization. Okay, and a possible result here, I just optimized 1 day of operation for this system, where we had a refrigeration supply of 7.8 megawatt hours, and in the not optimized stage we had 2.5 megawatt hours, which is then which shows an electrical efficiency ratio of 3.1. While not just taking into account the loading and unloading of the storage, which can be seen here on the left side, we could achieve a reduction of 0.2 megawatt hours and an increase of electrical efficiency, energy efficiency ratio to 3.4. And to explain it a little bit, so as you can see the blue line here is the ambient temperature, and the thermal load of the thermal storage follows this load, follows the ambient temperature. For example, at low ambient temperatures, as we would expect, the storage is loaded, and during high ambient temperature, the storage is unloaded. So when taking into account all other variables like the volume flows and the temperatures of the system, of course, the optimization potential is even higher. Yeah. Okay. That's so far from my side. It was very quick. And now I guess it's time for questions.
Thank you, George. Very interesting talk. Yes, we are ready for questions, and let me check Slido if there are any. So there are no questions from Slido. Among the participants here, may I ask if anybody has a question for George?
I could start with a few to start, okay?
Yes, please go ahead.
George, I completely agree with you. When the problem is that even a simple, or let's say a small system, is not simple at all, and when we use modern equipment, we have everything is variable. The compressor speed is variable, the circulation pumps are variable speed, everything is variable, and you can switch on off all the systems. So I really think that we need this kind of tool because the systems becomes very, very complex.
Yeah.
But the thing is that then the accuracy of what we are doing, exactly how we represent reality, and I didn't understand, because you have several steps of adjusting the model with reality. I didn't understand if in the end you try to do it, let's say, online in adjusting at the same time that you are recording data. I find that very, very difficult, because the conditions are changing in each component. So characterization normally is under steady conditions, so it is very difficult to do that. So you plan to do it in steps, or you plan to do it, let's say, really in time, the control. I think that would be very, very difficult.
Yeah, I totally agree. It's pretty difficult, but as you mentioned it, we are measuring every single component for its own. So the compressor with all his variables, the heat rejection with all variables, and so that the model is really adjusted to the reality. And
but my question is, do you plan to adjust it, let's say, in real time?
We have
in order
to
influence the operation.
So it's not really real time. So our time intervals right now are that we are collecting the data every minute. So in the end we have steady state models, but in a very short time resolution. So we are collecting this data every minute, so we can adjust the models, and then we can reduce we can use the time steps, since the polynomials are like continuous. So we can adjust our time steps according our calculation power in the end. So right now,
okay, but in the end they adjust. Okay.
Yeah, sorry.
I understand.
I think we can continue discussion after the presentations are done, since it's time for the next talk. Yeah, no problem. Thank you. So, since Professor Mykola Radchenko is here, may I just confirm that you'll be taking the questions for your presentation?
I have video presentation.
Okay, thank you. Okay. So let's start with the next talk, which is rational designing of ambient air conditioning systems of combined type.
Yes. Thank you.
And it is presented by Professor Radchenko. Just to briefly introduce Professor Radchenko, he is Professor Head of Conditioning and Refrigeration, Department of Admiral Makarov National University of Shipbuilding. He is Honorary Inventor of Ukraine, a member of National Commission of Heat and Mass Transfer of 2 scientific commissions of Doctor Science and academic degrees at Odessa National Academy of Food Technologies. He has several patents, books, as I can see, a list of 30 theses and many authored and co-authored articles. A super scientific advisor for the Verkhovna Rada Prize for most talented young researchers. Finally, he's also has scientific interest and focus on thermal power engineering, combined heat power generation, refrigeration and air conditioning. And he also works on heat and mass transfer in 2-phase heat exchangers, heat recovery in energetics, and from technology. So Professor Radchenko, please go ahead with your talk. Thank you.
Thank you. Good day, my colleague and friends. My name is Mykola Radchenko. I am a head of Conditioning and Refrigeration Department of Admiral Makarov National University of Shipbuilding, Ukraine. Let me introduce to you some results of our investigation in rational designing of 2-stage absorption ejector chilling system. The typical scheme of gas engine intake a cooling system with absorption lithium bromide chiller of a simple site is presented in this picture. Drawback of this system that absorption chiller is enabled to cool air below 15 degrees centigrade because of chilled water temperature of about 7 degrees centigrade. Traditional methods of air chilling system designing are based on current refrigeration energy production, independence of design refrigeration capacity, which are characterized by large fluctuation that enables to define exact value of design refrigeration capacity. The proposed method is based on annual refrigeration energy cumulative characteristic. Advantage of this method: the fluctuations of current refrigeration energy is considered by different rate of annual refrigeration energy production. This enables to determine a precise value of annual of design refrigeration capacity. The task of research are to develop a novel method of rational designing of air chilling systems that enables to define the rational value of refrigeration capacity that provides close to maximum annual refrigeration energy generation according to cooling needs without oversizing. To develop an extended novel method of distribution of the overall rational design refrigeration capacity between cooling load ranges for ambient air pre-cooling and further air subcooling covered by chillers of different types, to develop the scheme decisions of advanced two-stage air cooling by combined absorption ejector chiller. The main statements of research methodology are presented here. As a primary criterion, the annual refrigeration energy generated at refrigeration capacity according to current duties used as a primary criterion. The relative value of refrigeration energy referred to refrigeration capacity is used as indicator that enables to determine a precise value of rational design refrigeration capacity. In order to generalize the results of and simplify the calculations for any refrigeration capacity, the refrigeration capacity of chillers is used as a relative specific values per unit MS flow rate in air cooler, a specific refrigeration capacity. The corresponding equations are presented here, and for specific annual refrigeration energy production here. Here you see the results of calculation of rational and optimal design refrigeration capacity. This is the annual refrigeration energy production depending on design refrigeration capacity. This is the relative value of annual refrigeration energy production referred to design refrigeration capacity. As you see, the maximum of a relative value indicates the optimal design refrigeration capacity and corresponding annual refrigeration energy production. This curve corresponds to ambient air temperature to 10 degrees centigrade, to 15 degrees centigrade, and to 20. The rational value of design refrigeration capacity corresponds to second maximum of refrigeration energy production referred to design refrigeration capacity within the range of loading beyond the optimal value within this range. As you see, the rational value of refrigeration capacity is less than the maximum value calculated traditionally by about 15%. Here you see the results of calculation in relative values. As you see, this is a decrease in design refrigeration capacity. And in relative value, you see that design refrigeration capacity is less than maximum value traditionally calculated by about 15–20%. Here you see the two-stage ambient air cooling at the inlet of gas engine by absorption chiller feeding chilled water with temperature of about 7 degrees to high temperature air cooler where ambient air is cooled down to 15 degrees centigrade, and further air cooling down to 10 degrees centigrade in so-called low temperature air cooler by boiling refrigerant from ejector chiller. Here you see the results of calculation of rational distribution of design refrigeration capacity in two stages. This is the rational, the current refrigeration duties needed for cooling ambient air to 10 degrees centigrade, and this is for cooling ambient air to 15 degrees centigrade. As you see, the fluctuation of current refrigeration loading are caused by fluctuation in ambient air pre-cooling down to 15 degrees centigrade. As you see, the range of subcooling air from 15 to 10 degrees centigrade is respectively stable as compared to its fluctuation during ambient air pre-cooling to 15 degrees centigrade. So it's necessary to share the overall rational design refrigeration capacity for overall system into stable range for air subcooling from 15 to 10 degrees centigrade in ejector chiller as an example, and for quite unstable range for pre-cooling ambient air to 15 degrees centigrade. You see, this quite changeable range of ambient air pre-cooling is covered by absorption chiller, and the stable range of cooling needed for subcooling is covered by ejector chiller. Conclusions. The rational designing of air conditioning system provides a decrease of installed refrigeration capacity, chiller and air chilling sizes by about 15 degrees centigrade. The novelty of the methodological approach is that the fluctuation of the current refrigeration energy production are considered by the rate of the annual increment in response to refrigeration capacity needed. The advanced methodology of air conditioning system design includes additional stages focused to determine an optimal refrigeration capacity, providing the maximum rate of annual refrigeration energy increment and minimum sizes of air conditioning system accordingly, and a rational refrigeration capacity, providing a close to maximum annual refrigeration energy production without system oversizing. The scheme decisions of advanced two-stage air cooling by combined absorption ejector chiller with absorption chiller for ambient air pre-cooling at varying cooling loads and ejector chiller for further air subcooling within practically stable cooling load range that provides 50% increase annual refrigeration energy generation in temperate climatic conditions due to deeper cooling. The application of combined two-stage intake cooling is especially expedient for operation in temperate climatic conditions, providing about 50% increase annual effect in the form of refrigeration energy generation in the case of air conditioning systems, of fuel saving and power energy production due to deeper intake cooling in combustion engine. Thank you very much for your kind attention. Any questions? You're welcome.
Thank you, Professor Redchenko.
Thank you.
I'm trying to share my, okay.
Thank you.
So online there are no questions, but let me ask the panel here if there are any questions. We have about 2 minutes.
Well, Professor, if I can start, thank you for your presentation. It is a complex system, so it is difficult to understand. Sorry. Why the system is like it is? So why you have this chiller and then you have the absorption chiller? So it is the one that you have, and then you have to optimize it. Because so I wonder why that concept of the combination of those two systems.
Yes, I see. You know, absorption chiller is able to cool ambient air, absorption chiller of simple cycle, not lower than 15 degrees centigrade. And for temporary climatic conditions in Central Europe and in European countries, it's not enough. We have shown that we are able to increase the effect due to cooling about by more than 50% by deep cooling from 15 degrees centigrade down to 10 degrees centigrade or even to 7 degrees centigrade. And the fact is gained not only this 5 or 7 degrees centigrade lower temperature, but duration of operation machine at this lower temperature, you know, for temperate climatic conditions. So it's very important just to cool in temperate climatic conditions down than 15 degrees centigrade to 10 or 7 degrees centigrade. Of course, in hot climatic conditions, the effect will be not so high as in temperate climatic conditions. So I a bit wonder why in, for example, in Belarus, they mount absorption chiller, only absorption chiller with cooling ambient air to 15 degrees centigrade. It's not enough, you know. Okay. And if we use, of course, two-stage absorption chiller working at vapor, of course, we can lower temperature down than 15 degrees, maybe to 10 or even 7 degrees centigrade. So in our case, I propose to pre-cool ambient air down to 15 degrees centigrade at changeable climatic, changeable current lows by high efficient absorption chiller. And in the stable range of load down from 15 to 10 or even more, we can use ejector refrigeration chiller, you know, and he is working effective only in a stable range. So we could cover all this loading range with high efficiency. So in the first point of our presentation, you know, that we propose rational designing of such system according to annual refrigeration generation. Okay, thank you very much.
Thank you.
Thank you. I have a small question to ask, which is based on the air load. So in your paper, you mentioned that you classify the heat load in terms of stable and unstable patterns. So because the unstable pattern by definition itself is not well defined. So how do you take that into account, the unstable part?
Yes. You, I have shown, you know, we first of all we have to find this threshold temperature for dividing for unstable and stable range. So I showed that this temperature is about 15 degrees centigrade, you know, and all temperature, all load above this is extremely unstable, you know, and it could be covered by high efficient. And lower, it's it could be covered by for example, even vapor compression machine working at nominal load.
Okay, thank you.
Thank you.
Any other questions?
If I can, Professor Rodenko, is you have concentrated, let's say, on the ambient temperature variation, but what about humidity? So if ambient humidity changes, you also have a change in latent heat. Maybe that also will influence the let's say, the optimal sizing.
Oh, yes, I see. You know, we in our investigation we deal with ambient air cooling as the first stage in any central or combined system. As in combined system, it's outdoor air processing unit, and then in outdoor air processing unit we have to provide stable temperature at the inlet of indoor processor units. So all our efforts to provide this stable temperature, you know, for example, 15 degree or even lower. And then we can use this approach, you know, not only for our ambient air pre-cooling, but for indoor. I mean, this variable refrigerant flow system, you know, consisting from outdoor unit and indoor unit, and we can use for both of them. Thank you.
Okay, thank you very much.
Thank you, Professor. Our next talk is timetabled for 4 p.m. So should we wait, or if you have any questions for other talks within this?
The presenter is present.
The presenter is here, and I think it's a recorded session.
Okay, perfect.
Yes, Michael, should we go ahead with the next one? Or should we wait till 4 o'clock?
Good evening, everybody. In this presentation, I want to show the optimization of transport characteristics of auxiliary flows in horizontal pipe. This representation includes introduction, experimental device, experimental results, and conclusion. So, one, there are several ways to approach the emission problems from refrigeration. The most important is to minimize the charge in the refrigeration system needed to generate a certain refrigerating effect. 2. Indirect system with secondary fluid circuit make it possible to reduce refrigerant charge of 5 to 15% of the charge in system by using a compact factory-made design of the refrigerant circuit. 3. Secondary fluid is indirect system used to transfer or remove heat from the cooler user or heat source to the evaporator of the plant. 4. Auxiliary is a secondary refrigerant. It is a fast-changing refrigerant made up of millions of ice formed and suspended within a solution of water. 5. This work aims to present the influence of initial MPG concentrations and the ice friction on transport characteristics of auxiliary in horizontal pipe. The experimental setup is composed of two parts, the production part and distribution part, connected together by a storage tank. This figure shows the variation of the transport capacity in kilowatt of cooling at full melt-off in the pipe versus the velocity. For the 5 fixed initial concentrations of MPG and varying ice friction. These figures show the linear dependence of the transport capacity with the average velocity. One can observe that the transport capacity increases with increasing ice friction and the initial MPG concentrations. On the other hand, one can observe clearly that the level of increasing of transport capacity for a given ice friction to another is higher up to an initial MPG concentration of 14%. So there is an important latent melting heat of ice. In these figures, the required pumping power of the 5 fixed initial MPG concentrations is plotted versus the velocity. One can observe the linear dependence of required pumping power with velocity. One can also observe the required pumping power increases with increasing ice. However, the rate of increasing of pumping power of the ice friction to another is less up to a certain ice friction. It starts to increase rapidly. The values of this ice friction are 10% for 5% MPG, 20% for 11% MPG, 20% for 14% MPG, 13% for 19% MPG, and 10% for 24% MPG. This suggests the existence of local maximum for transport capacity and pumping ration at a certain velocity. While for circled curves the pressure drops are very high at low velocity, this can be interpreted by the ice slurry structure and different interparticular forces such as London van der Waals. That's why they have ruled out optimization. And in order to optimize the property of the ice slurry, the relation of the transport capacity to the pumping power given as a function of the velocity has evaluated. From these figures, we could derive the maximum ratio, which the correspondence of ice concentrations and the velocities for different MPG concentrations. We have included the result on the following table. As can be seen, all two flow velocities offer high ratios, but be aware that the velocities that are too low are not desirable from an operational point of view as these flows. And in order to avoid fast separation, the minimum rate was calculated from Gilbert equations, who recommends dimensioning the pipes in order to avoid velocity lower than twice the minimum velocity. So the velocity of flow must be less than the minimum calculated velocity. As can be seen on the table, up to a velocity of 1 meter per second, that is to say laminar regime, we have 5% MPG gives the poor result due to high pressure drop despite the velocity of flow is greater than the minimum velocity. 11% MPG concentration yields the best result due to low pressure drop with the velocity of flow is greater than the minimum velocity, of course. 14 and 19% MPG risk of blockage or sedimentation because the velocity of flow is less than the minimum velocity. 24% MPG gives infinitely lower ratio due to high pressure drop despite the velocity of flow is greater than the minimum velocity. Finally, the velocity must be kept as high as possible but always in laminar mode, which means the velocity up to 1 meter per second. If minimum pumping power is desired, the flow velocity should be kept as low as possible, but still sufficient to meet cooling needs and above minimum velocity to avoid system blockage. In general, with regards to the transport characteristics of the ice slurry, it can be recommended that for the ice suspension based on MPG as a solid, the initial concentration of 11% gives the best result because it exhibits the lowest pressure drop at the velocity between 0.2 and 1 meter per second regardless of the ice friction. Thank you very much. I remain disposable for any questions.
Thank you, Professor Mallory. Can you confirm that your audio is working so that we can ask questions? Hello, Professor Mallory. Can you confirm your audio is working? It looks like she is not able to connect, but we can proceed with the...
Michael is sending some information to her to solve the problem. I saw a message from Michael to her. So just wait a minute. The thing is that she has to connect the audio to the when she connects to the computer or the mic. Otherwise, she will not be able to talk.
Meanwhile, just to confirm, there are no questions on Slido. Okay, thank you, Michael. We can start the group session of questions for everybody in this refrigerants and technology session. And if Mallory is able to join, then we can continue with questions for her. So may I ask Professor Corbian if you have questions for anybody else?
Well, I had some for Suela Malari, so we wait for her. But for the moment, I think we can follow with some questions to the others. I think you mentioned that you have some for Taliesin. I didn't remember, sorry.
Yes, so Maxim, I have a question for you. So in the paper, you say that based on the analysis, you propose typical measures to improve operational efficiency. Can you give us some examples of what these measures are?
Yes, but it's not connected with this article, but we have which we optimized system for supermarket, and we decided to reduce energetic losses due to throttling. We use a cycle with economizer, and we can calculate how many energy we can save. Second one, it was when we try to not right word, when we use CO2 systems. And CO2 has properties that they have very big losses due to throttling. And that's why...
because of high pressure.
Yes. And that's why we use ejector systems and so on.
So basically you address the system level data and provide based on that.
But actually we, we're just starting to implement it to industry. And unfortunately, I don't have enough experience for it. We have just started.
Okay, thank you. Yeah.
And another comment I wanted to make to your work, Maxim, is that you are, let's say, taking into account the minimum condensing temperature that the manufacturer states for the compressor. But the thing is, I always have doubt about that information. A lot of times, they give a value because they have to give a value, but they are continuously changing they use the same compressor for different refrigerants. So I'm not so sure that those limits are very, let's say, accurate. So maybe you could work with those compressors at lower condensation temperature. So have you checked with the manufacturer if those values that they provide to you or they are in the documentation of the compressor are very accurate or are really a requirement?
It's a good question. Very good question. And I'm not ready to answer these questions. And that's why, because we have limit for measurement, it's what talking George Benz about it. And actually, standard system we use in Russia for hyper and supermarket, we measure just between 5 to 15 minutes. One measure per this interval. And it's very difficult to understand whether we lower or higher limit.
Okay, yeah.
It's kind of integral. But it's a good question, but now I don't have solution for it.
Yeah,
Thank
there
you.
is uncertainty with that. I have a question for George.
Yes, I'm here.
Okay.
Yeah, thank you, George. So you showed nice data related to what was difference between original system and the optimized system. My question is related to this optimization model that you have. Does it sit in hardware in the entire rig, or is it done as a software?
It's actually implemented in an virtual or in an virtual server. So we have a virtual server on the large calculating center of Munich. And so this virtual server it operates like all the time. That's and it don't need to be shut off. So he can run all the time. He can do all times like 24 hours a day or 7 days a week. He can measure the data, calculate it, and send it back to the system.
So your regression is continuously updating itself to match with the.
So the regression right now we are doing like every 10 minutes. So we have for every component we do a regression every 10 minutes. So which is like it's pretty calculation power expensive, of course, but and the big problem is like to sort the measure values. So you not only need the continuous values, you also need the binary values to know which component is operated right now and in which condition it's operated. How are the valves in the system and that stuff? So first thing you need to go to a selection process. Which component is active right now, and then you can do a specific measurement on the component itself.
Yeah. And my second question was, do you do an initial study on the degree of freedom of this optimization task and try to narrow down on parameters that are more sensitive, or is it including everything?
It's actually including every variable speed drive. So every degree of freedom we had taken into account, and it's combined by switching on and off each component and every variable speed drive.
Okay, thank you.
And of course, so the volume flows are important, but not that are not that sensitive. Don't have this high impact because the operation range is pretty limited. But what is of course the most beneficial optimization is to optimize the condensation temperature.
Yes.
Yeah.
But this 0.2 megawatt hour is definitely a big saving that you achieved.
Yeah.
Yes.
For doing nothing. I mean, doing nothing in the end.
Putting the system.
Yeah. So the calculation power loss is of course lower than the saved value of electricity. Yeah.
Thank you.
I have a curiosity about the algorithm. Why you use the one you are using? First thing is that it is integer. So I mean, this is probably due because you are playing with variables which are on off, and but there are other softwares use what they call, for instance, in MATLAB they use these discrete events, which is more or less the same thing, and now there is a suite of other optimization algorithms, genetic and other evolutionary things. So why you chose the one that you are using?
Yeah, I mean, you are perfectly right. So this system can be also solved with genetic algorithms, but we always want to have it we always wanted to have the opportunity to calculate it backwards. So we never wanted to lose the opportunity to calculate the system.
Okay, that's a good point.
The genetic algorithms, they are pretty fine if the system is too complex to calculate. But the validation of the results are much more easier when you're using a conventional algorithm. Yeah.
Okay. Michael is telling us that she already has the audio, so we can. I think she's already online. Maybe.
Yes.
Could you
Hello,
check
Professor Mallory. Can you unmute your and should we ask you questions? She seems to have lost audio connection again.
Okay.
Any questions for Professor Radchenko?
You're welcome.
If not, thank you, Professor. We can go to Maxim. Any questions for Maxim?
Thank you. Thank you very much.
Thank you. No. Any questions finally? Doesn't look like. So, Professor Corbian, do you agree we can summarize this session and end it?
Yes, Sam. So I would like also in your name to thank all the participants. You have all been very o'clock, so this help us to keep the schedule. And well, I think all in all has been an interesting session, and it has been a pleasure to meet all of you. Unfortunately, not in real conditions, but at least see your face. Okay, so
yeah.
Thanks a lot, and it has been a pleasure to meet all of you.
Yeah, thank you, Professor Corbin.
Thank
Also, thanks to Michael Tomlin for arranging and making this streamlined for participants too.
And thank you all for your participation.
Thank you.
Okay. So
Bye.
with this, I think we can close the session here, and just remind you that there are other sessions running, and we have the closure of the conference at 5 p.m.